Java. Okay, a few of the guys. The rest, you're studying some other programming language, like Python or .NET. Python. Okay.
No questions? You need markers?
No, not really. Sure. Most of the stuff is on the slides, so.
Anyway, before we start, let's say Happy New Year to everybody. We're quite excited today. Hope we have at least 2 talks. Hopefully we're going to have 3 talks. We're talking with Rimus from Tokyo, and I hope we'll have his presentation. I think we're quite excited to have Martin here. Martin is from the Bulgarian Java user group from Sofia.
Yep.
And they are quite active. I think they are quite more active than the corresponding Greek one.
Well, that's over the last few years. I mean, I just spoke with Nikos. You'll have some tickets for the Java conference, which we organize in May. So if you guys are interested in anything Java related, it's end of May. Weather is sunny. There are a lot of activities organized. So
I can tell it's a very nice conference. I was there last year, J Prime. We're gonna have our Vasilovta. We have Vasilov this year. So whoever wins the coin is going to take one of the tickets that Martin is going to use. It's a very nice conference. Sofia is only 3 hours drive from here. Are you going to be in the same place as last year?
Yeah, it's the same place as last year.
Be careful, Google Maps is not the best guide to there.
Yeah.
I ended up in a government building with armed people looking at me.
Yeah, it's next to the military museum.
Oh, that's why. So I had to drive with the car. I think we're with Christos, right?
Yeah.
But anyway, the place is really nice. It's a very large conference. If you can, please to go. Maybe we should start because we have 3 talks and we need to finish at some point, and probably you have more questions to ask. Thank you very much for coming. Let me take my glasses and Martin.
Yep. I can maybe try out the audio, or if we're going to do that.
I think don't
or
worry.
It's okay.
Recording you there. Say hi to Facebook.
Okay. Hello.
Okay.
Okay, we start.
Yes. Let me turn the lights on.
From me also, thank you for coming to today's talks. I hope you enjoy this one, although most of the things I'll show you are really bound to Java. Many of the concepts really apply to any programming language. It's not really a general purpose security talk where you listen mostly about things like DOS attacks and things like this. I'll show you basically what's the current state of security in the Java platform, what are the latest enhancements done in the JDK in terms of security, and we can also have some discussion and I can show you some extra stuff even after the session. Just a few short words about me. My name is Martin. Just until recently I was working as a freelancer on a variety of projects, mostly in Europe, through my company called Coffee Cup Consulting. Now I'm working as a Java architect for a company, US company, that has an office in Sofia called Resolve Systems. I'm one of the guys that organize the events of the Bulgarian Java user group, where we have this Java conference called J Prime, which runs for 2 days end of May. And for those of you that are interested, you'll have free tickets so you can attend the conference. We typically gather once or twice a month doing some sessions or just informally drinking beer, talking about Java and technology and other non-technology related topics in general. And I'm also trying to contribute to some open source projects. In particular, I'm very interested in OpenJDK and Oracle database, so if you have some questions in that area, we can discuss them. I'm also working on several security related tools. One of them basically is a small tutorial that tries in a very simple form to show you the main concepts of security related to the JDK platform. You can find that tool on GitHub, and in fact I can show it to you very briefly. So if you clone the code, you can basically play around with the tool, or you can use it in any possible way as you would like. It's a very simple, I would say, swing-based application where you have, in different sections, you have the different JDK APIs and different concepts outlined. You can go, for example, if you want to review what's the sandbox model in the JDK, you can go to the sandbox model section, and with some basic animations and examples, you can review the main concepts of security in the JDK. I'm actively working in this tool with the possibility to provide some exercises and some easier way to learn the concepts. So at that point, this tool mostly provides a basis for a tutorial for the JDK security portfolio. So yeah, if you're interested from the materials presented from today's session, you can also take a look into that tool. It's on GitHub. I guess Nikos will also share you the slides after the session. Okay, so going back to the presentation, just recently I also wrote a book about RabbitMQ. I'm quite fond of message brokers, so if you're interested in also going into some discussions in regard to this, we can have it, and I can also share you a copy of the book if you're interested in this area as well. In today's session, what we're going to talk about is, first we'll review what's the Java security model, how did it evolve throughout the versions of the JDK, and how you can use it up until now. Then we'll review some of the security aspects related to latest versions of the JDK, in particular to the new module system. In JDK 9 we have a new module system introduced in the JDK. Then we'll go and review what are the security APIs in the JDK. Apart from the security sandbox model that's built in the JDK, you have a number of utilities you can use to provide security for your applications. And we'll provide a review of those utilities and how you can use them. We'll also review what are the latest security enhancements in the JDK, in the latest JDK versions. And in the end, we'll review some best practices when you design and implement your applications. Some security guidelines for you to keep in mind when you write your code. So let's start with discussing what's the Java security model. That's really the essence of the talk, where we discuss what's the general model and how you need to understand it in order to know how does the Java security model work. So traditionally, software companies try to protect their assets, whether that's software, hardware, or anything, using some strict physical and network access policies. For example, the company tries to provision different kinds of tools like firewalls, IPS, IDS systems that try to detect some kinds of attacks occurring on the company's premises, and other kinds of software and hardware that facilitate the process of securing those assets. However, over time, more and more technologies become available for users through the browser. For example, more than 15-20 years ago, when JDK 1.2 was out, many people started implementing different forms of applets that can run in users' browser, like games or some kind of utility programs, where you go to the browser, play around with the program, and you can do something. However, running Java or any other kinds of programs like Flash and things like this in the browser provides a whole new range of security attacks, because pretty much those programs that run in the browser have access to your PC, and they can do things like deleting files, opening network connections, and things like this. And this was a problem basically that was not initially thought about, and it had to be addressed in some form in the JDK as well. So running those programs from the browser needed to be restricted in a way so that you can provide security for the users that run those applications. And the goal of the Java Security Sandbox model is to allow untrusted code running from those applets or managed applications to be executed on a user's environment, like the user's browser. And when it all started in JDK 1.0, the Security Sandbox model of the JDK was very, very simple. You just had the JVM running on your browser, and all the classes and the code loaded from the JDK, the utility classes, were deemed as system code, or which was trusted. So basically, any utilities like file streams, logging utilities provided by the JDK could do anything with the file system on your computer. and all the applets loaded from some location, let's say from seres.gr/demoapplet website, if you load some applet, all of the code from that location was deemed as untrusted. So we just had two domains, trusted code and untrusted code. It was as simple as that. However, this was not very flexible. So, you know, trusted code was given anything with the system, and untrusted code basically was a subject of some restrictions. And for that reason, in JDK 1.1, you had the possibility to provide some of the applets as trusted, meaning that if you sign an applet, digitally sign an applet, it is deemed as trusted. It can do anything with the target system. So in some cases, for example, the company might say, okay, this applet is a trusted applet. It can delete files on my system. It can do whatever it like. So I need to make it trusted. However, this model is still fairly simple. You still have trusted and untrusted domains. Okay? And these are just the steps that you can use to sign an applet. As of JDK 1.1, you can do that with latest JDK versions. So you compile the source code for the applet, the Java source code. Then you create a jar file for the applet. You generate some set of public-private keys that you can use to sign the applet. Then you sign the jar file with the private key. Then you export a certificate for the public key. You import that certificate in the Java Trust Store as a trusted certificate. So the JDK and the JVM running on the browser can use that certificate. You create some policy file with the restrictions that apply to those applet, to that signed applet. And finally, you load and run the applet. These are the steps that you can use to sign an applet. As of JDK 1.2, there was a radical change in that thinking, in that particular security model. So what we showed earlier was fairly basic. You just have trusted and untrusted code. However, this was not really flexible, so there needed to be a way to specify which applet has what permissions to do with the file system. And the ability to specify permissions based on the applet was based on the location from where that applet was loaded from. In that particular case, I load my applet from some particular website. In that case, it's SerresTech.gr. And based on that location, I specify some permissions in a so-called security policy file. This security policy file comes with the installation of the JDK. So by default, you specify all of those permissions in that policy file. Here I say grant code base, then the location of where my applet or set of applets is loaded from. And then I specify the permissions that I grant to that applet. In that particular case, I grant the possibility to delete the C Windows folder or any subfolder inside of it. As you can see, this is a much more flexible security model introduced in JDK 1.2, and that security model is the one that remains until latest JDK versions. It's not changed up until today. And in order to enforce those permissions specified in that policy file, there were two new utilities introduced in the JDK, which are called Security Manager and Access Controller. They pretty much do the same thing. So Security Manager utility just uses behind the scenes Access Controller, because Access Controller is a newer API than Security Manager. And they provide a series of check permission methods that enforce those permissions specified in the security policy file. We'll go into more details on how those two work, but for now you can think that as of JDK 1.2, the basis of the modern security model in the JDK is introduced, and that's more than 15 years ago. So you can imagine that this security model is fairly old, but it applies up until today. So the security model becomes more code-centric. You specify for what location of your applications. I'm giving applets as an example, but this applies for any kind of Java application, like, for example, an OSGI, Java EE application, any kind of Java application that can be bundled in some standard format like a jar file, WAR file, or something like this. So now additional security decisions are specified in this security policy file that's provided by the JDK, and there is no more notion of trusted and untrusted code as it was with earlier JDK versions. However, something new is introduced, which is called protection domain, And the idea behind protection domain is to bundle the security information for a particular class in your Java application. Every class in your Java application has a protection domain, which contains the location of where that class was loaded from, whether that was the file system, whether it was a network location or something else, and also the set of permissions that apply to that Java class. And these are the permissions specified in that security policy file, based on the location of where those classes are loaded. And we have two types of protection domains, system and application. The system protection domain is the domain of all the classes that are provided by the JDK. The system class is provided by the JDK, and the application protection domain. And in order to get the protection domain for any class in your application, you can say get class, get protection domain, which gives you a protection domain object that wraps the security information for the class in your application. There are some properties, interesting properties that apply to the permissioning system in the JDK, such as, for example, if you specify one permission, it may imply another permission. For example, if I specify that I may delete the C Windows folder, this automatically implies that I may delete the C Windows System 32 folder or any folder inside C Windows. And also one location of where my code is loaded, where my application is loaded, may imply another location. If I specify permissions for some web location like SerresTech.gr, this implies that this set of permissions apply for all the applications loaded from SerresTech.gr/demoapplet. So these are interesting properties of the Java security model that allow you to minimize the set of security information that you specify in the security policy file. Now that's a bit of a more complex concept, but since the execution thread of your application may pass through multiple classes loaded by different class loaders, this means that at a certain point in time in your application, you might have code that's been executed and passes through multiple threads and multiple classes that are loaded from multiple class loaders. You know, all the classes in your Java application are loaded by a particular class loader. And for that reason, since your execution thread passes through many classes that may be loaded by multiple class loaders, you might have multiple protection domains on your execution path. And now the question is how we can determine the protection domain or the set of active permissions that apply for the currently executing code. And the rule of thumb identified by the JDK is that the set of permissions that apply at a particular point in time in your application is the one that's the intersection of all the protection domains through which the current execution passes. So for example, if in your application you want to do a permission check at a certain point, let's say you want to write to the file system, and in your application you say security manager.check permission, what happens is that the current call stack is taken and the protection domain from every class in the call stack is retrieved, and an intersection is made basically on all the permissions in that protection domain, and that's the set of permissions against which we check whether our currently executing code has the possibility to achieve something. I'll give you some more concrete examples on this. But for now, as we said in JDK 1.2, the security sandbox model of the JDK is shaped. In JDK 1.3 and 1.4, some extensions to that security model are introduced, such as the JAS framework. JAS, or Java Authentication and Authorization Service, is a framework that allows us to provide authentication and authorization capabilities in our Java applications. And that framework basically extends the syntax of the security policy file by providing the possibility to specify also permissions based on the user that's executing your application. So you can provide some authentication mechanism that logs your user, for example, using a database, some GUI interface where you need to specify your username and password and so on. And based on the attributes assigned to that user, you can specify some permissions. In that particular case, I define an attribute for a user that's specified in an Active Directory or an LDAP server, where basically pretty much most companies keep their user information in some form of Active Directory or an LDAP server. So I specify that if the user that's running the application has this LDAP attribute, which is some name equals to Tom, then that user is able to delete the C Windows folder. So as of JDK 1.3, basically, you can combine the information of who is running the source code and where that code is loaded from to create some forms of permissions for your application. As you see, the model becomes more flexible. You can use more attributes to define the permissions for your application, like the attributes of the currently logged in user. So for JAS, it extends the security model with role-based permissions based on the logged in user, and also the protection domain for all the classes in the system may also contain information about the list of principals or attributes of the user, such as username, email address, some LDAP attributes that are specific to the permissions applying for that particular class in your system. It's another dimension basically in the protection domain. The authentication component of JAS that allows you to provide authentication mechanisms for your Java application, such as I mentioned, for example, you may specify that you authenticate users against a relational database, graphical user interface, and so on, is pretty much independent of the security sandbox model in Java. You can use it directly as a framework or as a library in your Java application. And typically, JAS and the authentication component of JAS is used in a much wider context like Java EE application servers, any other kinds of applications. Okay, and how JAS works basically? The core classes of JAS are, first we have a login context. This is the root class of the JAS framework. You start by using a login context that reads information about the different login modules that you identify in your system from a configuration file. A login module basically implements a way to authenticate users against a particular external system, like I said, a relational database, an LDAP server, and so on. The JDK provides default implementations for different login modules. We have some for logging users against a relational database or against a Windows domain, and so on. So the login context basically reads information about those login modules from the JAS configuration file to determine how to authenticate users. When a user is authenticated, there is a subject instance created representing that user, and that subject instance may have one or more principals which are the attributes of the user, such as username, email address, and so on. And based on those attributes, permission checking in the JDK is done. So if the user has certain attributes, you can specify certain permissions on the users that execute your application. So up until JDK 1.4, to provide a summary on how permission checking is done, we'll go through the following flow. We'll discuss right from the beginning what happens when you start your application. So first, when you start your application, it runs without a security manager installed, meaning that the security policy file is not checked at all. By default, all the Java applications that you write and don't have a security manager are not the subject of permission checking. And it's pretty much something we all start with. We start writing Java applications, and they can do anything with the file system, unless there is some enforcement at the operating system level. I can delete any file, open network sockets, do whatever I like. But if I run a managed environment like a Java EE application server, or my application loads some external applications, it's a plugin application that loads plugins, I may install a security manager by calling the system.setSecurityManager method and specify an instance of the security manager class. The security manager, as I said, is responsible for enforcing permission checks from the security policy file in the JDK. And I can also specify my security policy file by calling policy.setPolicy. If I don't do that, by default, the default java.security file is read, which resides in the JDK installation. So my application starts up, it installs some security manager. At the second step, the JVM starts loading the classes for my application, or the process of class loading kicks in. Before actually class loading happens, a number of other things happen, like for example bytecode verification. The JVM makes sure that the bytecode for my application is valid, it doesn't violate the JVM language specification. And this is really a preliminary security check to make sure that someone hasn't tried to maliciously change the bytecode of my application, or my application doesn't try to break the JVM in which it is deployed. After bytecode verification is done, class loading kicks in, and it loads based on the source code of my application. It creates the class instances in the JVM, and it sets also the permissions and the set of user attributes based on the security policy file of the JDK. So basically, the set of permissions is for each class in my application is set during class loading. When some system code is invoked, like for example, I tried to write to the file system, open a network socket, behind the scenes the JDK is using the installed security manager to do permission checking. Many of the classes in the JDK have calls to make sure that the particular utility has the permission to do something. For example, if I try to use a file output stream to write something to the file system, and I have a security manager installed, the JDK checks that I have the permission to write to that particular location. It uses a file permission and the security manager to enforce that permission. And based on that, the JDK makes sure that the particular permission is enforced. And if I don't have the permission, I have a security exception from my application. My application can also do permission checking on its own. So if, for example, if I run an application server or any kind of Java application that needs to do permission checking, I can do it on my own. In order to do that, I need to create an instance of the Java permission for which I need to check whether it applies or not. In that particular case, I create a socket permission that checks whether I'm able to connect or accept connections from SerresTech.gr's website on ports 8000 to 9000. This is the permission for which I'm going to check. And at the second step, I take an instance of the security manager class by calling system get security manager. At that point, I might not have a security manager instance installed in my JDK application. And if that's the case, I don't do permission checking. That's the default behavior. So I need to make sure that I have a security manager instance installed. And if that's the case, I call the check permission method. This check permission method is really the core of the Java module, the Java Security Sandbox model. What it does here, it takes the current call stack with all the classes involved in my current call stack, and for all of them, it takes the set of permissions from the protection domain of those classes and checks whether that protection domain has the socket permission which I have specified here. And this is how the security model works. If that's not the case, if that socket permission is not provided in that protection domain for all the classes in the stack trace, I get a security exception. This is what we already mentioned. And applications can also do security permission checking, not only using a security manager, but also an access controller utility. The only difference here is that access controller provides static methods, so you don't need to have an instance installed in your system. You can just call the static methods from access controller to do permission checking. Here is the same example, but with access controller. As you can see, here I can use a static method called check permission from the access controller class without having the need to install an instance of access controller in my application. And I can also do some other interesting things if I need to. I can change the currently running user, for example, calling the subject.doAs static method. And by dynamically changing the user that runs the application, I can invoke certain code with different privileges. I can also do privilege escalation by calling the doPrivileged method. I do permission checking based on a restricted set of permissions. The doPrivileged method basically skips the entire call stack up to the point of calling doPrivileged. So it doesn't check any of the permissions provided by the call stack outside of this doPrivileged call. In doPrivileged, I specify a block of code that is privileged and that executes the particular code with escalated privileges. That's very useful, for example, to give you more understanding on why this is useful. For example, imagine you have an application server, a Java application server that provides you with the possibility to write some log files to the system. And that, however, writing log files to the system requires you to have write permissions to the file system. But all the applications deployed on that web application server don't have the permission to write to the file system. And if we try to do the writing using that logging service, we'll get a security exception because those applications don't have permissions to write to the file system. And what the application server needs to do it needs to make a do privileged call in the logging utility, so that we skip permission checking for all the applications deployed in the application server. And this is an example of why we need privilege escalation. For example, to enable users dynamically to achieve something that's typically not allowed in the system. And that's also useful by hackers, for example, that try to make some use of utilities on which they don't have permission, but they try to escalate their privileges by changing the currently running user or do some other trickery to escalate their privileges so they can run the code in an escalated mode. And the security model defined by the security manager is quite customizable. You can create your own way of doing permission checking. And this is what Oracle database does, for example. There is a JVM running in the database that allows you to write Java stored procedures. And that JVM basically can do permission checking based on permissions specified in a relational database table, not in a security policy file. And that for that reason, Oracle database provides a custom implementation of a security manager that does the permission checking against the relational database table. That's an interesting application of that security sandbox model, but you might find another needs for that. So the security model provided by security manager is customizable. You can implement your own way of doing permission checking. Moving forward, in JDK 1.5 and 1.6, there are not many major enhancements to the security model. There is, for example, support for LDAP in JAS. For example, you can do authentication of users against an LDAP server. In JDK 1.7 and 1.8, where the majority of probably Java applications are staying up until today, because many applications still haven't migrated to JDK 9, but that's a separate topic. So as of JDK 1.8, there are some further enhancements like additional methods provided to the security manager and access controller utilities, such as, for example, the ability to call a do privileged method and check only against a certain subset of permissions. So you don't escalate the full set of permissions, but you just specify a list of permissions which you provide in that privileged block. In JDK 1.9, which was released fairly recently, a new module system was introduced. Has someone heard about Project Jigsaw or the new module system? Or has someone used some form of a module system like OSGI? I know Nikos has worked on an OSGI project. So basically the idea here is fairly straightforward, just to take your application and split it into smaller modules. Before JDK 9, you typically do that by splitting your application into separate Java projects and you compile them into jar files, you create some common libraries that you use and so on and so forth. But over the versions of the JDK code base has increased drastically. We have more than 5,000 classes in the JDK itself. So one of the ideas of the teams working on the JDK in Oracle was to get all of those 5,000 classes and split them into smaller modules. So you can install not all of them in the JVM, but just a subset of them. For example, you only use the logging module of the JDK. You don't need JDBC, you don't need any other modules provided by the JDK. And for that reason, one of the main efforts here was to split the JDK code base, which is a big ball of spaghetti, into different modules, which was a fairly big effort. And this effort basically took quite some time. And now in the JDK, we have 50 plus modules that you can use. By default, you can run your JVM with all the modules installed, or you can just use a bare simple JVM and install the modules on demand. So the idea in JDK 1.9 was mainly to split the JDK into modules and also provide simple utilities for application developers like us to split their application into Java modules. And splitting the application into Java modules basically might also be a subject of specifying different permissions for your modules, for your application modules. And with the introduction of the module system, basically, the same security model that we just reviewed applies for Java modules. So in the same manner, you can specify as a code base a Java applet, a jar file, a war file. You can specify in your security policy file a module on which the security permissions apply. And to give you some more example on this, So this is, for example, you're running JVM. You have some system modules like Java logging. Java base is the base module provided by the JVM that provides the bytecode interpreter and the core of the JVM. And let's say you have your own custom module, which is gr.SerresTech. This is a model of your application that provides some utilities, let's say. Then if you want to specify permissions on that Java module, you can do that in the Java security policy file. The syntax is slightly extended to support a new protocol format, which is called GRT, which stands for Java Runtime Module. And using this GRT protocol, you can specify the module currently running in the JVM on which you specify certain permissions. In that particular case, on the SerresTech module, I specify the possibility to delete the C Windows folder. So you can see that even with the introduction of Java modules in latest JDK versions, the security model is untouched. But there are just some slight extensions that allow you to provide permissions based on this new way of packaging your applications. And there are some security implications with the introduction of Java modules. So now that the system code is split into modules, the code of the JDK is split into modules, and applications can use a minimalistic version of the JDK that doesn't run with all the 5,000 plus classes. You of course can imagine that this improves the security of your application, because there might be some security issues with some of the utilities provided by the JDK, but if you don't run them in the JVM, you don't have any security issues, of course. And also your application code is split into modules with stronger encapsulation at runtime, meaning that modules provide an extra layer of encapsulation in addition to what you already have in Java, such as the different access modifiers like public, protected, private, and package access. And Java modules provide you with one more layer of encapsulation of your applications, which improves the security, of course. Access control, basically, this is a very subtle difference, but it's worth mentioning, is that access controller for Java modules is not based on a single class loader that loads the classes of your module, but one Java module might have different class loaders loading the classes of that Java module. And the protection domain for the Java module might be governed by multiple class loaders, not just one. And there is an additional way to specify encapsulation using Java module. That's by means of exported and open packages. In the module meta information, if you don't specify which packages are visible to the outside world, which packages your module exports, all of the other packages that are not exported are encapsulated in addition to what we have with the access modifiers, meaning that this export way of specifying which packages might be imported by other modules is an additional layer of encapsulation which improves security. Open packages is something which provides slighter restrictions. It specifies if a package is opened from a module, it means that you can retrieve it using reflection in another module. So it means that basically you can still use that package even if it's not exported using reflection. You can dynamically define Java modules. There is a new method called getModule introduced on every class in the JDK. You can retrieve the current JDK module in which the class is defined. There is something called module layer, which is just a way to group modules logically in the JDK. So you get the module layer for that module, and you can call the define modules method where you define dynamically your Java module in your application. And here, when you define the module, all the restrictions specified in the security policy file, the security restrictions, might apply for that dynamically created JDK module. That's a bit more involved concept. You'll probably never need to define modules at runtime, but it's good to know it's possible. So this was for the JDK sandbox model. Before we proceed with looking into what are the security APIs, do you have any questions or something that's puzzling you in terms of the security sandbox model? Yeah, we have some.
First,
You're Nikos.
Yes.
Okay, so I want to ask about the security policy file.
Mm-hmm.
So this policy file leads to a web server, for example,
Mm-hmm.
and give the permissions to web server,
Mm-hmm.
right?
Well, the security policy file is local to the JVM. Where you install the JVM, it's a file which basically is in the installation of the JDK. I'll it's better if I show it. For example, if I've installed on a server on my machine the JDK, let's say I have probably 6 or 7 Java versions here. I'll go to JDK 8. If I go to lib, no, just a second to remember where was that. No, it's better to go to here. And let me just look for. So it's in JRE lib security, we have java.policy file. And if I open that, I can manually here add the permissions that I want. By default, if I install a security manager, there is some set of permissions by default which are granted to my code. Such as, these are property permissions that allow me to retrieve these system properties in my code.
Yeah.
But here I can specify the permissions applying to my classes.
So my question here is, when someone, let's say that this file is the web server.
Mm-hmm.
Okay. So,
do you have a JVM running on that web server?
Yeah. Can I access it from a web browser and edit it or something like that for the security reasons? You know, it lives inside the JVM, right? It lives inside the JVM, and the JVM has its sandbox and all this stuff.
Yeah.
So the problem here,
you want to remotely change the policy file somehow.
Yeah, for not good reasons.
Yeah.
You know, for not good reasons. Maybe this kind, because I don't know what the security policy does. Maybe it's an open port to outside because it lives there, you know?
By default, this is not visible to the outside world. There is nothing that provides with the capability to modify it externally. So this information is visible only locally in the running JVM, but there is no open port from which you can access a user interface to modify this. In the JDK, in older versions, there is a utility, a GUI utility provided by the JDK called Policy Tool that provides you with a simple GUI interface like the one I showed you earlier with the Swing application that allows you to modify that application. I think I can show you that utility in JDK 1. The thing is that in latest versions in JDK 10, this utility was dropped from the JDK distribution, probably because people don't use it much. But this utility, this policy tool is this one. If you run it, here you can see quite a dummy looking application provided by the JDK where you can load the policy file and you can modify it. So I'll open the policy file from the JDK. What? Oh, okay, my PC is hanging a bit. Or the application just crashed. I think it's the application. I'll probably kill it, open it again. What I'll do, I'll open the policy file just to show you how you can modify it from this tool. Lib security. And here you can add entries using this simple GUI editor and things like this. So this is one way system administrators can modify this policy file. Typically developers are not willing to do so and to touch and play around with these permissions. It's more for system administrators to specify the set of permissions on running Java applications. But by default, you cannot edit it externally unless you provide some other way to do that, like through a web service or something like this.
Yeah, the web service maybe have access to JVM.
Yes, yeah.
Okay.
Yeah. Nikos?
I haven't used JVM, I have used Shiro, so I experienced some
Yeah, Apache Shiro is like a framework that allows you to provide security in your application.
Regarding the policy file, is it read statically once when the class loads, or is it if it changed while the class is running, do you get updated?
So by default, basically, when you write the policy file, the idea is that you write it once at the beginning, and permissions are not reloaded because loading of that information from the policy file happens during class loading. But for the purpose of permission checking, some latest enhancements, like for example, there is a secure class loader. For example, if you use JAS, you cannot do that information because your user, when class loading happens, you don't know who is the user because he is not logged in yet. So if you specify permissions using JAS, then if you specify those permissions later after your application has started, the check permission method consults dynamically the policy file. So you can modify it dynamically if you specify permissions based on the user that's executing the application. But if you specify permissions based on the location of where your classes are loaded from, then this happens statically and it's not reloaded after.
How would you handle the fact that, I don't know how the policy file handles the fact that sometimes permissions change dynamically. I mean, you log in as a user, you set of permissions. However, throughout the lifetime of the application, the user is elevated or gets access.
Yeah.
How do you do that design-wise? Is it something that you have to put in the policy file, or can you read dynamically policies from databases?
Well, typically what's being done in the majority of cases up front, you identify, okay, this is the set of permissions I need to apply based on the location of the applications or the set of current users I have in the system, let's say administrators. They might be logically grouped based on some attributes. And typically up front, you design and specify those permissions in the policy file. You do some basic testing that really those permissions are enforced. But over time, if you decide that in production for some users, for example, you need to remove some permissions or add some more permissions, you do that by just going and specifying them in the Java policy file. And this will be dynamically reflecting when permission checking is done specifically. Because as I mentioned, some of the permissions, like for example, if you specify them for principals, when you call the check permission method, it dynamically consults the security policy file to do the permission checking. It's not that everything is loaded up front when the application is loaded. So you can do that typically. Yeah?
One more question. So the main problems with security is to access the file system or open check an open port or something like that. Only those two?
Well, in the JDK we have by default like 20 plus permission categories defined. All of them are instances of the permission class, java.security.permission something. Some of them are file and socket permission. We have these property permissions that are specified by default. We have also some permissions related to reflection, whether you can define dynamically classes in your application, or if you are allowed to install a security manager, and things like this. But typically, extensions of the security model, like in OSGI, for example, they define an extra set of permissions that allow you to achieve certain level of activity. In OSGI, for example, you can register and retrieve services from an OSGI service registry, which is a very dynamic way to create publish-subscribe mechanism. And in order to be able to do that there, OSGI defines, for example, service permission. Or in OSGI you have, because the OSGI specification defines certain level of managing OSGI modules or bundles, it defines permission that allow you to install or uninstall bundles in terms of bundle permission. So by default, the JDK provides a default set of permissions, but extensions on top of that security model provide their additional implementation of permission classes, like the OSGI framework does. Although OSGI provides a much more flexible security model on top of this one, which, for example, allows you to deny users certain permissions. As you can see here, the security model is you specify what is a user allowed, but you cannot say, for example, I want to allow the user everything except something. This is something you cannot do that in the JDK by default. Okay. If no more questions, we can proceed with the second part. So on the other side of the coin, apart from the security sandbox model, we have a number of APIs we can divide in several categories of utilities you can use directly in your application, even without taking into account the Java security sandbox model. For example, if you want to use some cryptography utilities, you want to create your own, let's say, certificate authority that issues certificates and things like this, you can use a number of utilities. And roughly speaking, we can divide them into those categories. You have the JCA, or the Java cryptography architecture, which provides you with utilities to use different kinds of cryptography algorithms like message digests, cryptographically strong random numbers, and things like this. You have PKI utilities, which allow you to use or to validate public certificates, to create public key authorities, and things like this. Basically, these are utilities that allow you to manage and to work with SSL certificates. You have the JSSE, or Java Secure Socket Extension APIs. This works in a manner very similar to standard Java sockets that allow you to create client-server communication in your application. But JSSE basically is an extension of the standard Java socket mechanism that works over TLS to basically enable secure communication between parties. The Java GSS API, it's basically an alternative way to establish secure communication channel. It's an alternative to JSSE, and the Java Security Services API works by means of exchanging security information in a security context between the client and the server. So it provides security information using a security context that is exchanged between the parties. And for example, one of the main uses behind the GSS API is to enable, for example, Kerberos authentication. For example, if you want to, from your Java application, to authenticate against the current user on a Windows server, the Kerberos protocol works by means of exchanging secure information in a token-like manner. And the JDK provides integration with Kerberos through the GSS API. And we have the Java SASL API, which is called Simple Authentication and Security Layer. The SASL API allows you to exchange security information between parties. Let's say a client and the server want to start communicating by authenticating a user from the client to the server. And the client says, okay, I can provide you with a username, email address, and let's say a phone number. How do you want me to provide you this information for authenticating? The server says, okay, give me the username and the phone address so I can authenticate you. So the SASL API allows you to negotiate, to provide a mechanism to negotiate the way the client and the server exchange security information by first negotiating what kind of information needs to be provided between the client and the server. So in a summary, let's go briefly through each one of them and see what it provides. So the JCA, or the Java cryptography utility, it's a provider-based API, meaning that the JDK doesn't give you concrete algorithm implementations for working with the cryptography API. There is a default implementation of some basic cryptographic algorithms called the Sun JCA provider, which is for quite some time shipping with the JDK, but there are other third-party security libraries like Bouncy Castle, for example, that provide implementations for security algorithms for the JDK cryptography providers. And those providers allow you basically to use different kinds of algorithms to create digital signatures or message digests, to use different kinds of cryptographic chiffers, both symmetric and asymmetric, and use other kinds of cryptographic services, like, for example, the ability to generate cryptographically strong random numbers. The JCA, as I said, has a pluggable architecture. You can implement your own set of algorithms and provide that using the security configuration in the JDK, so it can be used by your application. As I'm speaking about JCA, it would be good if I show you how you can specify that information in the JDK. So let's say you implement your own cryptographic algorithm. You go to Jerry, lib,
security, and there is a Java security configuration file here, where you can specify the providers or the classes that provide the implementations of your algorithms here. For example, if I want to see some of them here, for some algorithms we have here like 10 registered providers that give me different kinds of cryptographical algorithms. Most of these are
provided by the JDK. So here you can specify security provider .11 equals some of my classes that provides cryptographic algorithms. There are quite some extensions to the JCA API. Latest versions of the JDK enforce some additional usage of more cryptographically strong algorithms through the provider API. The other utility is for dealing with public certificates. So the set of PKI or public key infrastructure utilities provide you means to work with public certificates, certificate revocation lists, and OCSP protocol. These are two mechanisms that allow you to verify whether a certificate is valid. For example, it hasn't expired, it's not stolen, or things like this. Which basically allows you to interact with the certificate authority that has issued your public certificate. So these are mechanisms that allow you to validate that the certificate is indeed still valid. And the PKI utilities also provide you with mechanisms to persist and store information about those certificates in key stores and trust stores in the JDK. By the way, does someone know what's the difference between a key store and a trust store? So a key store basically is used to store information about your public-private keys for your certificates, so you can retrieve and use them. And a trust store is used to store information about the trusted certificate authorities that you use to validate your certificate against. So in the trust store, in the JDK by default, we have a trust store called CA-certs file, or certificate authority certificates. So in that JDK trust store, you can import all the certificate authorities that you use to validate your public certificates. And in the key store, you store information about your own certificates. That's the difference. And here is in this picture, using the PKI utility, it's not related basically to the JDK, but it's a general way of how you can do certificate revocation checking. So you have your own public certificate, and either using a list published by the certificate authority or an endpoint that uses this OCSP protocol, you can validate that your certificate is valid against the certificate authority. Moving forward, the JSSC API, or the Java Secure Socket Extension API, is an implementation of the TLS or SSL socket series of protocols that allow you to enable a secure communication channel. As you know, TLS is the de facto standard protocol used to enable secure communication between any kinds of endpoints. TLS is also used to implement the so-called SSL VPNs that allow you to, for example, to connect to your company's infrastructure from home. And the JSSC API basically provides implementation of TLS in the JDK. And some of the major enhancements in terms of security in latest JDK versions, as we'll review them briefly, are related exactly to the TLS protocol and the JSSC API. The Java GSS API, as I mentioned, provides an alternative of JSSC for secure socket communication. And you can think of it as a framework for providing token-based security services that allow you to exchange secure information between parties using a security token. And the Java GSS API can be used in combination of JAS to provide you with additional services for example, authenticating against a Windows domain. The Java SASL API, last but not least, as I said, is a protocol for exchanging authentication information. And it's a framework where basically you can use different providers, SASL providers, to enable different kinds of authentication mechanisms between your client and server by negotiating also what kind of security information you exchange between them. And yeah, the SASL API also continues to be enhanced in versions of the JDK, like for example with additional possibilities to exchange authentication data between the client and the server. Now, having spoken about the APIs in the security APIs in the JDK, let's review briefly what are the latest security enhancements related to those APIs in latest JDK versions. So you basically get an idea of what's the direction of where the security improvements in the JDK are moving toward. So in JDK 9, released just recently, we have additional support for the DTLS protocol. So the JSSE or the Java Secure Socket Extension API by default before JDK 9 provided support for only for TLS, which runs on top of TCP protocol, which, as you know, is a reliable protocol that allows you to, for example, retransmit packets if they fail, and also provides you with additional failover mechanisms. And the DTLS protocol allows you to enable SSL over applications running on top of UDP, which is an unreliable protocol. So D stands for datagram TLS protocol. There is a specification, distinct specification running on top of that, and it provides additional some differences with the standard TLS protocol, mainly related to the difference between the UDP and the TCP series of protocols. There is another thing called TLS ALPN extension. This is again improvement related to the way TLS handshake happens between the client and the server. The TLS ALPN, or Application Protocol Negotiation extension, allows you to negotiate what's the application protocol that will be used behind the scenes. And we'll review that briefly. I think I have some slides for that. No? So the TLS ALPN extension, for example, is very useful now with the new version of the HTTP specification, for example. You know that we now have HTTP 2.0 coming on the horizon, and there might be many web servers that support different versions of the HTTP protocol, for example, 1.1 and 2.0. But however, some clients might still be supporting only HTTP 1.1. Newer clients for example, newer browsers might support HTTP 2.0. So sometimes when you connect to a website, you're not sure which application protocol might be used, whether that's HTTP 2.0 and 1.1. And since basically going to most websites requires you to use SSL, during the SSL handshake process, the client and the server might determine which version of the HTTP protocol to use based on this TLS ALPN extension, which allows you to negotiate the application protocol during the SSL handshake. Another thing introduced in JDK 9 is called OCSP stapling. OCSP stapling is basically a way to do certificate checking not from the client that uses the certificate provided by the server, but by the server itself. If I go a few slides back, here on this diagram where I showed you how you can do certificate revocation checking, this is the Java client application that gets some public certificate from the server and it validates it against the certificate authority. But using OCSP, you can imagine that this might trigger a large number of requests from clients to the certificate authority, because on every single step a client might send a request to check whether a certificate is valid. In order to reduce that load to the certificate authority, client may delegate that certificate checking to the server, and that's called OCSP stapling basically. It's the server that does the certificate checking, not the client. Okay. And we also have something which is called PKCS 12 key stores. By default, before Java 9, the default format for storing information about public certificates was JKS, or Java Key Store. This was a proprietary format defined by the JDK to store information about public certificates. But this PKCS 12 is a much more general purpose specification that allows you how to store information about public certificates. And by moving towards this standardized format, you can provide more interoperability, for example, with other applications. For example, if you have a system with applications written not only in Java but in Python, .NET, and so on and so forth, if you use a PKCS 12 format, you can store certificate that can be used by all of those applications. If you were using older versions of the JDK and you specify your certificate in a JKS key store, in order to use it through a Python application, you have to export it first, convert it to a different form, and then use it in your Python application. So it's a nicer way to provide interoperability with JDK and other kinds of applications written in different programming languages. There are some other enhancements introduced in JDK 9 as well, such as another cryptographically strong implementation of that allows you to generate random numbers, cryptographically strong random numbers. There is some utilization of CPU instructions to use the Ghash and RSA algorithms in a faster way. This is more of a performance optimization. Also, something introduced is that SHA-1 certificates are disabled for certificate validation. So most applications moving towards JDK 9, if they're using SHA-1 certificates, they need to upgrade to a newer version of the SHA series of protocols to use certificates that use cryptographically stronger algorithms than SHA-1. And also an additional implementation of a SHA-3 series of hash algorithms, which are more cryptographically strong algorithms, is introduced in JDK 9. In JDK 10, less degree of security enhancements is introduced. The major one is that Oracle decided to provide their set of, or their list of certificate authorities that they partner with by default in the CA certs file. So before JDK 10, the CA certs file shipping with the JDK was pretty much empty. And as of JDK 10, you have some set of default certificate authorities. Also, there are some additional enhancements like the removal of some methods that were pretty much not used in the security manager class. Also, the policy tool that I just showed you earlier is removed as of JDK 10. I don't know why. Probably that because people don't tend to use that tool much, and they decided just to remove it. But you can still use it, of course, to modify. You can get it from an older version of the JDK to modify the security policy file. And also there is a removal of some deprecated classes under this package, CompSun security out. There are, of course, some more minor security enhancements, which I'm not going to discuss. That's why I'm calling these the highlights, because these are the more major security enhancements introduced by the JDK. And in JDK 11, really the major highlight is the support for TLS 1.3 specification. This is the latest version of the TLS specification, which introduces a lot of enhancements in the way TLS handshake happens between the client and the server. And if you're interested to see, basically you can go to the TLS 1.3 specification and review what are the changes introduced inside. We're not going to discuss them today in detail, but as of JDK 11, we have full support for TLS 1.3. So as you can see, most of 90% of the core enhancements in regard to security in latest JDK versions are related to TLS. Because it's really critical that nowadays all of the applications that you deploy and communicate with other applications have TLS enabled. And that's really one of the main focuses here, is that support for TLS is improved in the JDK. And now moving towards really the last section of our presentation. Now, having reviewed what is the security sandbox model, what are the additional APIs and latest enhancements in the JDK, it's worth revisiting some nice practices that we need to consider when we design and implement our applications. First of all, many of the guidelines related to security are really not bound to the Java programming language. For example, if you review a security presentation or a book, most of them speak about things like input validation, error handling, type safety, access modifiers, prepared SQL statements, and things that are really general practices not related to the programming language. However, for Java, we have some additional guidelines to keep in mind. As we were speaking about the security manager, when you write a Java library, you need to take into account that it might be running into an environment where security manager is installed. Meaning that you can write a Java library, and your library uses reflection, for example, to load something from the file system or to do something else. But if it runs in an environment where there is a security manager installed that doesn't allow you to do reflection, when you try to use your library, you might get some security exception. And this was the case, for example, I had a case where I wanted to use the JSON library, which is a library provided by Google to do marshalling and unmarshalling from JSON. So you can basically format your data through JSON, and from JSON you can create instances. And the JSON library was using reflection heavily to achieve that. And when I tried to use it as part of an OSGI bundle which I had, I got a security exception because my bundle didn't have the possibility to do these reflective calls. And the JSON library wasn't designed in a way to allow me basically to use it in an environment that was running with the security manager installed. There was a need for this library to be patched at some points. For example, doing some additional privileged calls inside the library, so it can be deployed and used in an environment with the security manager. Another important point is that all the permissions that you specify for your applications need to be minimal. In many cases, when you write your application, most developers want to do all permissions. So they set all permissions in the policy file and all problems solved, basically. You don't deal with security permissions and exceptions. However, you need to follow the principle of least privilege, which might be really annoying and sometimes might be difficult to identify all the needs for your application up front. So it's not always possible to specify all the permissions that your application requires, but you need to do that incrementally, specifying some permissions, seeing that your application needs more, and specify them on top in the security policy file, rather than granting all permissions to the code base, as it opens possibilities for security bugs. And yeah, of course, that's also not related to the JDK. Copy-pasting of code delegates security issues if you have some in the copied code. So that's why one of the additional reasons in terms of security why copy-pasting is not a good thing. You also need to sanitize exception messages. I guess many of you have seen a website when there is some error, you get 200 lines of stack trace from the website, which is really not very user-friendly. And in addition to that, it gives additional information about how your system runs, which might be used by malicious users. So you need to make sure that you provide sanitized messages to all the information returned to the user, but not Java stack traces. And that's pretty much it. Thank you for the attention. Now, any other questions related to security? If not, then we can also discuss them offline. I'll be here.
Regarding CSS, because I got bitten by that the first time I tried to use it, most of the programmers might not realize that they need a separate CSS file for the Java application. Especially if you're on Windows, you have a certain set of certificates of the Windows space. Everything might be working. But the Java application will not be that store.
Yeah, because you don't have the certificate authority listed in the CSS file. And if it's not listed there, you cannot use it to validate your certificate, and you cannot use your certificate. Okay.
Questions?
Yeah, you can find me here. I'll be here, and also on Twitter. I'm also on Twitter. Nikos can also give you my mail if you have some questions in regard to the topic of security. Yeah, feel free to reach out to me.
Thank you very much.
Thank you.